Hello, we are now looking at section 1.3 vector equation. So we will talk about what are vectors in Rn, the space Rn. So what is Rn? If you recall, if we just say have R, that is our real number line, single line. If we have R2, then we have two space or a Cartesian coordinate plane like over here, or we can have, depending on our variables, we can have instead of xy we can have x1 x2, so it is a two-dimensional space. It is also called two space. R3, which is our three-dimensional space, it is also called three space. It consists of three perpendicular axes, so three axes which are mutually perpendicular to each other, xyz, or x1 x2 x3, depending on our variables. So in Rn, so this is the n space. Now remember, we cannot draw or sketch or visualize our these spaces bigger than R3 because our universe is only three-dimensional. But we have problems which could be multi-dimensional, more than three dimensions. So we are discussing this theory of vectors. So in Rn, an n by 1 matrix, a matrix with only one column, is called a column vector. So a matrix with only one column, or simply a vector. So in textbooks, a vector is denoted by a bold letter. For example, whatever name we choose for the vector, we can notate it with bold letters. Now it's harder to write bold letters in our texts when we are writing. So we can use one of these notations where we have an arrow on the top or a bar on the top. Now if we don't put an arrow or a bar, it is not clear whether we are talking about a value or a number or a vector. So it's important that you put a bar or an arrow on the top of the vector. So the vectors in U2, R2 will look like this. Vectors in R3 will look like this, and vector in Rn, any dimension n, depending on the value n, will look like that. Another real example with real numbers in there. Now geometrically, vectors in R2 or R3 are represented by arrows starting at origin and ending at the point whose coordinates are given by the entries of the vector. So what happens if, for example, if we want to draw or graphically sketch this vector u, then we will correlate this vector with the point 2, -3. Now I'm not saying they are equal to each other, but from this vector is u is correlated with the point 2, 3, -3. So we will see now how we draw them or sketch them. So here I have two vectors. U I took it to be 2, 1, B to be -1, 3. So I draw my coordinate axes. Now the point 2, 3, 2, 1, is over here. So I plot the point and then I draw an arrow starting from origin to the point 2, 1. So this is the vector U. Vector V is -1, 3, and the point -1, 3 is over here. So I draw the point and then I sketch the vector by drawing a line from origin to the point -1, 3. So that is the vector V with an arrow showing that this is the vector V. Now in 3 dimensions, same thing we will do. Our vector will be a 3-dimensional object. There will be 3 entries in the column. So we can correlate it to the point 2, 3, 3, this triple. And then once we plot the point which is over here, then we can draw our line from the origin to this point, just to make it more clear where the line is coming or the arrow is coming. I have drawn this cube or parallelepiped. Okay, now we say that two vectors are equal if and only if their corresponding entries are equal. So we say if we have this situation that a1, a2, a3, a vector with these entries is the same as vector with these entries, if they are equal, this can only happen when a is equal to b, a1 is equal to b1, a2 is equal to b2, and a3 is equal to b3. Now note here that this vector has 3 entries, this vector has 3 entries, but they are not the same. Why? Because this is 3 by 1 and this is 1 by 3. So sizes are different, so they cannot be equal to each other. So we saw when what a vector is, how can we say the two vectors are equal, and the next thing, addition and scalar multiplication. So given two vectors u, v and a scalar c. Now we are going to look in R2 because it's easier to visualize or see what is happening there. But this operation, addition or scalar multiplication, they can be extended to Rn. So we have two vectors, one is u1 v u and the other is v with coordinates u1 u2 and v1 v2. So these are two vectors in R2 and c be a scalar. Then u plus v, the vector u plus v is the same as u1 v plus v1 and u2 plus v2, means we add the corresponding entries. And the vector c times u, now this is the scalar multiplication. So what happens when we multiply a vector with a scalar, with a number, that number gets multiplied with each entry of the vector. So this is how scalar multiplication is done. So now we saw how we can add vectors like algebraically or numerically. What about graphically, or what about geometrically? So there is something called parallelogram rule for addition of vectors, and we are going to look at it in R2 again because it's easier to comprehend it in R2. In higher dimensions, because we cannot visualize, so it will be harder to understand. But this can be carried out, the process can be carried out to Rn vectors. So if u and v are represented as points in the plane, so if you have a vector u, then you have a vector v. So let's say u ends up here. So it means if I draw the line, it goes like that. And let's say v ends up over here. This is v. So in order to find the u plus v, I should complete the parallelogram. So it means I should draw a line parallel to this line starting at this vertex, and then another line over here. So this is the fourth point. So 1, 2, 3, and this is the fourth vertex. So now the line or the arrow it joins from origin to this fourth vertex is the sum of the vectors u and v. It will become more clear in the next example. Now the zero vector is defined by 0 with a bar on top or an arrow on the top and has all entries equal to 0. So this is what a zero vector is. So for example, the zero vector in R2 looks like this, the zero vector in R3 is this, and the zero vector in Rn is that. So how do I add, or what is the parallelogram law? Here it is more clear. So I'm taking the same two vectors that we added previously. So u is 2, 1 and v is 2, 3, negative 1, 3. So u and v, you can see them in this diagram. So now what I did, I completed the parallelogram. So I drew the line over here, and then this one, this side. So then the vertex, fourth vertex I got here, and I join it from the origin, that is our u plus v vector. So the next thing we want to look at is what we call linear combination. So what is linear combination? So if we have vectors like v1, v2 up to some number vk. So this could be 5, 6, 8, 9, 10, however many vectors in Rn. Now note here, there is no relation at this moment. We say there is no relation between k and n. K could be less than n, k could be more than n. So we say that there are, if given v1 up to vk in Rn, then and scalars c1, c2, c3 up to ck. So as many number of vectors, the same number of scalars. Then the vector y defined by y is equal to c1 v1 plus c2 v2 plus so on plus ck vk is called the linear combination of the vectors v1, v2 up to vk with weights c1, c2 up to ck. Now note that the weights in a linear combination can be any real numbers including the 0. So for example, we can have, if we have two vectors v1 and v2, so we can have another vector 3v1 plus 2v2. Another example, we are now again dealing with three vectors v1, v2, v3. So we can have half v1 minus v2 plus 5 over 2v3. Or we can have a vector like this, 2v1 plus 0v2 plus v3. So you see, we can also have a 0 as our constant. Now up here, the one I have here, this is called a vector equation because we have the y equal to this quantity. Quantity on the right, that is what is the linear combination. This is linear combination. So what it's showing when I say y equal to this quantity, y is equal to this linear combination, it means y is equal to, or y can be written as a linear combination of v1, v2 up to vk. Okay, so same thing I have repeated here. We can cross it, or this is just a repetition. Okay, for example, if we are asked determine whether a vector b can be written as a linear combination of the vectors v1, v2 and v3. So we are given v1, v2, v3. So here v1, v2, v3, and we want to see if the vector b, which is 2, negative 1, 0, this one, can we write b as a linear combination of v1, v2, v3. So what this means is that we want to find out if there exists constants c1, c2, c3. Why c3? Because there are three vectors v1, v2, v3, so we need three constants c1, c2, c3 such that b is equal to c1 v1 plus c2. So this will be not go up to ck but only finish at c3 v3. So c1 v1 plus c2 v2 plus c3 v3. That is what we want. Now when I expand it, let's see what happens. What do we mean by c1 v1? This is c1 v1. This is c2 v2 and this is c3 v3. So we want to see if this adds up to the vector b, which is over here. So I wrote it like this. Now if I use the scalar multiplication, each of these constants in front of the vector will go to each entry. So the first vector, this will become over here. So using the scalar product or scalar multiplication, the first vector becomes c1 minus 2c1 and 0. The second vector becomes 0, c2 and 2c2. And the third vector becomes 5c3 minus 6c3 and 8c3. And the right hand side is b, which is 2, negative 1, 0. Now because this is just the sum of the vectors, the three vectors are being added over here, so I'll add them and I get this. So the first component is C1 plus 5C3, and the second is negative 2C1 plus C2 minus 6C3, and the third entry is 2C2 plus 8C3. So now notice this is one single vector. So when we added those three vectors, we got one vector, and we are saying it is equal to 2, negative 1, 0. Now by the equality of the two vectors, each entry must be the same corresponding entries. So first entry over here should be the same as first entry here. So that is what I wrote over here. In the same way, we put the two second entries equal to each other and the third entry. So what we get is a system of linear equations. So what does that show us? I haven't actually solved the problems, but what I have shown you here is that solving a vector equation is the same as solving a system of linear equations. And now, how to solve a system of linear equations? This is something you have learned in section 1.1. So, solving a vector equation is the same as solving a system of linear equations. So, what do we mean by solving a vector equation? Usually, when will we be solving a vector equation? If we are asked a question that is a vector y or is a vector b can be written as a linear combination of the vectors v1, v2 up to so on, or we can have some other name a1, a2 up to so on, an. Okay, note here from the above example that I showed you, we can say that a vector equation, which looks like something like this, has the same solution set as the linear system whose augmented matrix is this, where the first column is the v1 vector, entries of the v1 vector, second column is the entries of v2 vector, and so on. Vn is the entries of the vector vn, and then the entries of b will be the last column. So in particular, what we say is that in particular we can say that b can be generated by a linear combination of these vectors if and only if there exists a solution to the above linear system. So in other words, if the above linear system has a solution, then we say that the b vector can be written as a linear combination of the columns of the matrix, or we can augmented matrix, or we can say that b can be generated by a linear combination of the vectors v1, v2 up to vn, if and only if the solution to the above linear system exists. Okay, the next new concept is span v1, v2 up to vk. So k is again some number. So span of these vectors. So what do we mean by that? So basically, if we have v1, v2 up to vk are in Rn, now again note here n and k are different. So for example, in R3, we can have, so n is 3, but if we are looking at a1, a2, then my k is 2. So I have two vectors, so k is 2. If in R2, 3, I'm looking at a1, a2, a3, then I have three vectors, so k is also 3. But if I'm looking at a1, a2, a3, a4, then I have four vectors, k is 4 while n is 3. So they can be different. They don't have to be the same. They can be same or they can be different. So we say if v1, v2 up to vk are in Rn, then the set of all linear combinations of v1, v2 up to vk is denoted by the set that is contains all the linear combination is denoted by span v1 of v1, v2 up to vk, and it is called the subset of Rn spanned by these vectors or generated by those vectors. So this is a new concept, spans of vectors. So in other words, we can say that span of these vectors v1 up to v2, this is this is the collection of all vectors that can be written as in the form c1 v1 up to ck vk for some scalars c1 up to ck. Because for every vector, those scalars will be different. So note here, this is important. Asking whether a vector B is in span of these vectors is equivalent to asking whether the vector equation this has a solution. But this vector equation having a solution means, so we say, or equivalently asking whether the linear system with augmented matrix v1 up to vk, then the b column up because it's augmented, has a solution. So in simple words, if you are asked to this question, that to determine whether b is in span of some vectors, what we do is solve the linear system with augmented matrix, and then if it has a solution, we say that that yes, B can be written as a linear combination, and if the augmented matrix gives us there is no solution, so we can say that the vector B cannot be written as a linear combination of these vectors. Okay, I will stop here and rest I will talk in next video.